And then I was like, lay in bed till 4. And then I'm like, well, I'm awake now. Like, I'm not any closer to sleep than I was an hour ago. So I got up and I did some work. Okay. All right, that's recording. Let's make sure the sound is on. Yes, sound is on. Yay. Okay. Thank you.
Faster than your friend, the hole gets larger. If your friend
Okay. So we're just going to watch and then we'll fill it in. If you want to fill in as we go, that's okay, but just don't miss things because you're like, yes? Okay.
In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed,
what happens to the size of the hole if you're working at the same speed? Stays the same. This is called an equilibrium. Is this a static equilibrium where everything is unchanging? Or is it a dynamic equilibrium where there is change happening? Dynamic, because the dirt in the hole is new dirt sometimes, right? Sometimes it's this dirt, sometimes it's that dirt. Yes?
there would be no change to the size of the hole. The same concept can be applied to a reversible reaction.
What is a reversible reaction? It can go forward and it can go backward.
If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium.
So that's like when we're filling the hole at the same rate as emptying.
This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process.
Hard to reach an equilibrium if you can't go backwards. Yeah? If you're only allowed to dig the hole will only get bigger.
Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter.
So there's no exchange of what? Matter. But what happens with energy? Let's find out.
Only exchange of energy.
Energy can go in and out. That means you can heat it. That means you can put it in an ice bath and cool it. Okay?
An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container.
Can you guess what those would make? Hydrogen iodide, HI. Okay? So right now, all we have is reactants. Yes? So what reaction is occurring? The forward reaction or the reverse reaction right now? Forward, because we only have reactants. Can we go backwards if there's no product yet? No.
To produce hydrogen iodide.
Oh, look, now we have some product. Could we go backwards now? Yes.
At the start of the reaction, there is a high concentration of hydrogen and iodine.
See how there's a lot? A lot of reactant.
And the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring.
Okay, so this is just like the hole where you don't see the size of the hole change because somebody keeps putting dirt in, but someone also keeps taking dirt out. So some of the HI turns into H2 and I2, but at the same time, other H2 and I2 molecules react to make HI. Does that make sense? Yes? Okay. And if they're happening at the same speed, then you're at equilibrium. You will not see any change. Everything will look the same.
Action has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened?
What do you think would happen if we opened the lid to the glass jar? Talk to your neighbor about that. Remember, these are all gases. All gases. So what happens when we open this jar? The gases just... Can we be at equilibrium if everything is floating to this end of the world and that end of the world? No, because then the reactant particles aren't near other reactant particles and the product particles aren't near other product particles, and so nothing can be in equilibrium in an open system if things are escaping.
Please pause the lesson to think about this and resume when you are done.
We already did that. Sorry, yes. As long as, if it's a gaseous system, it has to be have a lid on it and be closed. If it's an aqueous system, it is closed by definition because ions don't jump out of solution. The closed system would be the liquid.
If it's like gases and it's open, so the reaction is not gonna work.
Pretty much, yeah. You can't reach an equilibrium. I mean, yeah.
If the lid was removed, the system is no longer at equilibrium, as the reactants and products, or matter, would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature.
There's a word for you, equilibrates. If you don't like that word, you could also say forms an equilibrium with gaseous bromine. So
remember that this is not a reaction, but rather a phase change.
What's the difference between a reaction and a phase change? Yes? Yeah, you still have the same elements. The particles are identical. So you would still have Br2 in liquid form, and you would have Br2 in gaseous form. Sorry? Yes, liquid nitrogen is still N2, and that would just be a phase change going from liquid to gas. Yes?
Can we see that the phase change only the kinetic energy, the reaction with the
Not really. No. In a phase change, during the actual change in phase itself, it's all a change in potential energy as bonds are breaking. Yeah? And so if you actually measure the temperature, say you take some ice and you melt it, it's all going to stay at 0 until it's all melted, and then the kinetic energy will go up. Yeah.
Phase changes can also reach equilibrium under the correct conditions.
What are the correct conditions? The system has to be closed.
As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously,
what does simultaneously mean? At the same time.
At the same rate, there is no observable macroscopic change.
Now, they didn't write macroscopic, but macroscopic means things that macro, what does the prefix macro mean? Big. So these are things like, if I look at this water here, macroscopic properties are like, it's colorless, it's liquid, things I can observe. Yes, it takes up this much volume. Those are all things I can see. Are the particles moving around in here? Yeah. Yes, but can I observe that? No, that's not a macroscopic property. You can observe it. Okay, well, good for you. That's fantastic. It's got X-ray vision. No. All right. So macroscopic is things you can actually observe, whereas particle level, there are still changes happening. This water, like if I let it sit, it looks like nothing's moving. But if I were to look at the particle level, I would see particles moving. Yes?
So something that a dynamic equilibrium, that means that no change is brought upon like the sort of system. Like for example, like in some cases that you can, if you want to reverse directly, you can like put it up on the stuff, right?
You can make the equilibrium shift to new positions, and we'll talk about that another day, not today. Okay?
But the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
Okay, so we are going to now go and fill everything in together, because why not? Imagine you are digging a hole. As you are digging the hole, your friend is refilling it. If you are digging the hole faster, whoops. If you are digging the hole faster than your friend is refilling it, the hole gets bigger. If your friend is filling in the hole faster, the hole gets smaller. If the two of you are working at the same rate, there would be no change to the size of the hole. In this analogy, does the digging of the hole represent the forward reaction or the reverse reaction? Forward. Filling the hole then must represent the reverse reaction. The speed of digging represents the reaction rate. The hole getting larger represents the concentration of products getting larger. The hole getting smaller represents the concentration of products getting smaller. The same concept can be applied to a chemical system. Or a reversible reaction. I don't know which one it was. They both work. If the rate of the forward reaction, in other words, reactants turning into products, is the same as the rate of the reverse reaction, products to reactants, what do we call this? Not just an equilibrium, dynamic equilibrium. Oh, the reaction is said to be at equilibrium, sorry. Because both processes are occurring simultaneously at the same time. Even though there is no overall observable change. Is there change? Yes, there's change at the particle level. Okay. Now, just in case, if you ever miss anything as we're going through this, you can go back and watch the video, or in your answer key, you'll notice it says 1.1a filled in. Guess what is in there? The blanks filled in. So if you don't want to watch the whole video and you miss something, you can just go and look in the answer key, okay? All right, for a chemical system, such as a what is a chemical system? A chemical system could be a reaction. Okay, so the system is the reaction. Or if it's not a reaction, it could be a phase change, a physical change. You have two important criteria that were given in the video. Do you remember the two of them? It must be a reversible process. If it's not reversible, obviously you can't reverse it. Shocking. And it must be taking place in a closed system. A closed system is one in which there is no exchange of matter. So matter can't go in, matter can't go out. What can go in and out? Energy can go in and out. I actually got some people asking about that in the reaction rates section. They were like, hang on, when you heat that up, that means that the kinetic energy went up. Doesn't that mean that the potential energy had to go down? But if you're heating it up by putting it on a hot plate, the extra kinetic energy is coming from the hot plate, not from the reaction. Does that make sense? Yeah, okay. So the energy can go in and out if you put something hot underneath it, or if you put it in an ice bath, okay? Then it's going in and out of the system. Although the video does not mention it, there are 3 other criteria necessary. That gives us 5 criteria in total that we need in order for a system to be at equilibrium. First of all, you have to have both reactants and products present. How could you have a reverse reaction if there were no products? How could you have a forward reaction if there were no reactants? It just makes no sense, yes? A lot of these things are fairly obvious, okay? What does temperature do to rates? It either increases it or it decreases it depending on what you do to the temperature. The key thing is that it changes rates. If you are changing the rates, are the forward and reverse rate going to be equal? No, okay? There are circumstances where you can make them both faster by the same amount and both slower by the same amount, but temperature actually changes forward and reverse rates differently. So temperature has to be constant, otherwise you're going to be moved out of equilibrium. The rates will no longer be equal. Yes?
So you mean like we don't need to wait for the forward reaction to happen the product and then go to the reaction?
It depends. It depends on when you start looking at the system. Did you just dump some reactant into the vessel? Then there's only forward and you're not at equilibrium yet. Okay, so you have a reversible reaction that could take place, but it's not happening yet. Okay, so to be at equilibrium, you have to wait, like if you just put reactant in there, you have to wait until there's product as well, and the two rates are equal. Yes?
Why does equilibrium occur? Like, why does it do that? Why does it
Because there is a push from nature towards the lowest potential energy state. That's number one. Okay. There is also a push from nature towards the most disordered state, towards the most chaos, the most randomness. Okay. That's called entropy, if you've heard of entropy. Okay. And when you have potential energy pushing one way, or enthalpy pushing one way and entropy pushing the other way, you get a reversible reaction. And the most stable state is occurred when the two rates become equal. Yeah? And we'll talk more about that later. Okay, for now, you just need to know to be at equilibrium, the temperature has to be held constant and the forward rate has to equal the reverse rate. If any of those criteria are met, not met, you are not at equilibrium. Okay? So, here we have some hydrogen and iodine in a flask. You'll notice the double-headed arrow. That means this is a reversible reaction. We'll often call that the equilibrium arrow. At the start of the reaction, we have only H2 and I2. So there is a high concentration of hydrogen and iodine. Now, if I've got hydrogen and iodine, what will they do? They'll bash into each other and do what? They're going to react. What do they form? Hydrogen iodide. As those H2 and I2 react and form H and I, what happens to the concentrations of hydrogen and iodide? They go down. So the concentrations of H2 and I2 both decrease. As hydrogen iodide is formed. And so obviously the concentration of hydrogen iodide, what does it do as we get the forward reaction happening? It has to increase, right? You started with none, it has to increase. Okay, and you can see at the start of the reaction, we've got all reactant. Later in the reaction, we have less reactant and more product. And finally, later on, we have the final equilibrium state, which happens to be wherever it is based on that entropy-enthalpy balance. Okay. As HI is formed, now we've got some HI. Once we have HI, what reaction is now able to take place? The reverse. Over time, the concentration of H2I2 and HI stay the same. Become constant, let's say that. Why is this not writing? There we go. Become constant. I think I like doing it during the video better. I did that with the other block. So what is happening here? The reaction of H2 and I2 to produce HI is occurring at the same rate. Thank you. I was like, what did I mean there? Same rate. So there are no observable changes. Although both the forward And just so you know, this is forward, FWD, and reverse, rev. Reactions are occurring. The reaction has not stopped. Even though you don't see anything happening, you're looking at it and you're like, looks like nothing's happening. It has not stopped, but rather, what has it reached? Dynamic equilibrium. We already thought about this. If the lid was removed, the system is no longer at equilibrium, since both the reactants and the products or matter would be able to escape the system. And here was that fun word. Liquid bromine equilibrates to form gaseous bromine at room temperature. Is this a reaction? It's not a reaction. It is a state change or phase change. Phase changes can also reach equilibrium under correct conditions. What are those correct conditions? We need to have, well, phase changes are all reversible. We need to have, the system must be closed system. What else needs to be true? All phase changes are reversible, so that's almost a moot point. We need to hold what constant? Temperature constant. As liquid bromine, what do we call it when it turns into gas? As liquid bromine turns into gas, what do we call that process? Evaporates. Okay, so as liquid bromine evaporates, gaseous bromine then condenses. Since these two processes are occurring simultaneously, at the same rate, there is no observable macroscopic change. But the system is in fact in dynamic equilibrium. So what was our summary definition of dynamic equilibrium? What did it have at the very first one? Oh, I should write it the other way around. Forward rate equals reverse rate. Yes? check the answer for you, but I'll get the last one wrong. That was bad. Oh, good, I'll take this answer key. It's the one with the weird statement. Oh. No, it's not here. Actually, 2.1.2a is not here. Oh, that sucks. Okay, forward rate equals reverse rate. There's no observable changes. The forward reaction and reverse reaction continue to occur. We're not going to watch the video. It was kind of fun, but I think we can do without it. There's some exercises. That's going to be your homework. What? Those whole 2 exercises. We got to write 8 things. Oh my God. Now, the main part of your homework is what? Study for your unit test. Do you guys know about spaced repetition? Spaced repetition is where you learn something and here's your memory. When you learn it the first time, there's your memory. Oh, I know all sorts of stuff. My knowledge is high. Knowledge. Okay? Now, what happens as the days go by? Now, it does eventually get to 0. And you'll notice it goes down pretty quickly. Now, if you study again, it doesn't go down as fast. And it doesn't go down as far. So if you study twice, maybe by test day, you're going to be here. If you study 3 times, every time you study the same material, your forgetting gets less and less. That's why your teachers are always telling you, study a little bit tonight, study a little bit tomorrow night. It's better than cramming it all in at the last minute, because what happens if you cram at the last minute? You are maybe here, right, on the day of the test. I assume that, yeah. I mean, honestly, I would do it on the day of the test, but I would also have done it here because I know I'm going off to university next year and I'm probably going to need to know this stuff. And if I've forgotten it all, then I have to relearn it. And I have to relearn it while I'm getting used to being in a new environment, while I'm learning to cook for myself, while I'm like living away from home for the first time, while I'm doing all these things which are very stressful. Whereas if I remember it, it's better. Yes?
You know how you could like mix some meat, like vinegar and make mustard gas?
Okay, we're going to talk about this later. No, I hear you, but we got through this in my other class, so we're going to spend the last 5 minutes doing this rather than mustard gas. Yes, oh my God, like suck it up, it's okay. All right, you're in grade 12, off we go. Most chemical reactions, this is on page 5. Just wait until you get to university. I had a prof who talked like this all the time, and his writing was like this, and I took 13 pages of notes in 50 minutes every class. So, one-way arrow. Yes? If we take some carbon, like some coal or something, and we burn it, can we get carbon, and we get carbon dioxide, can we get the coal back? No. This is one way. It only goes one way. You cannot unburn things. However, if we have NH4Cl, what's the name of NH4Cl? Ammonium chloride. Tell your partner if you can remember the names of the NH3 and the HCl. Hydrochloric acid, yes. Ammonia. Okay, so ammonium is NH4 plus ion. Ammonia is NH3 with no charge, neutral molecule. Okay? This is a reversible process. We sometimes call this a double harpoon arrow. If you don't know what a harpoon is, it's what whalers used to do to go and kill the poor little whales, or the poor big whales, I guess. Right? That looks rather tragic, but you can see we don't draw the full arrowhead. We just draw one thing that way and one thing that way. That is the reversible reaction arrow. Next page. Oh, we're not going to get through as much as we did with the other blocks. But we're going to get as far as we can. Okay? And then when the bell goes, I will let you go. We call this the forward reaction. These are our reactants. These are our products. This is our backward or reverse reaction. We still call these the reactants, and we still call these the products, because otherwise you would have to change what you were saying every time you said it. You know what I mean? Like you could be like, yeah. Whatever is on the right is the products. Whatever is on the left is the reactants. It doesn't matter if you're talking about the reverse reaction or the forward reaction. Whatever's on the left, reactants. Whatever's on the right, products. Now, we are placing some NH4Cl in a closed container. Here's my closed container. NH4Cl. How much NH3 and HCl is in there right now? How much? Whoops. How much? How much? NH3 and HCl is in here now. How much? None, because I didn't put any in, right? None. Not in that moment. Okay, so I threw some into the container of the NH4Cl. There's none of the other stuff because it hasn't reacted yet, and I'm flinging my glasses all over the place. Goodness me. So we have lots of NH4Cl. Lots. If you don't like the word loads. Loads is kind of a British term more. They like saying that. So the forward rate is fast because we have lots of reactant particles colliding. What can you say about the reverse rate? Remember, we have none of this. So what's our reverse rate like? There is no reverse rate. Well, or reverse rate is equal to 0, I should say. That's more official. There we go. Reverse rate equals 0 because we don't have any of our product yet. See? None. That doesn't happen. 0. So we're going to plot the first point on this graph and then we're going to be done for today. So if we are graphing on our y-axis, if we put the rate, just like we did in Unit 1, do you remember that? Rate went on the y-axis. And this goes on the x-axis. The initial forward rate is fast because we've got lots of reactant particles colliding. Yes? The initial reverse rate is 0, because we have no particles. And yes, that is exactly what happens. We'll get to that tomorrow, though, because the bell is going to ring in 30 seconds. Okay? Yes. No, probably not stupid.
Like, I'm pretty sure it's stupid.
No stupid question.
It's more than
You are told.
okay.
Okay?
You can't tell you are told.
You are told.
Yes.
You will be told a student places some NH3 and HCl into a flask. Or you'll be told a student places some NH4Cl into a flask. Or later on, you'll be told a student places this much of this, that much of those into a flask. And you're asked, are we at equilibrium?
Oh, no.
And then
Oh, just
we'll
What if you just ask the NH?
no, no,
Yeah.
or on its gas, flash, but if it's like something is shaking the system, it's probably gonna be over. What? Oh, wow.
So like one.
Yeah. Let's make sure.
Oh my goodness.
Okay, Tim, yeah.
Right, so if it's close, is it cool to tell us if it's reversible or not?
It depends on some class.
So like, because like.
Oh, show Abby. Show Abby. Why is this? It's gone. What?
Okay, and I'll let you know, I don't know, it's not water. But if it's not water, ask them to pay for it. But there are separating flows from the water.
Oh my God.
This mark, right. I promised my aunt, did you get your answer? Not really.
Because I don't know nothing but no mustard gas.
Yes.
I don't know. And you should be glad your teacher does not know how to make toxic gases.
Ask Mr. Weinberg. That's
Oh yeah, Mr. Feinberg will know.
I know.
I feel like his integrity is probably well capable of being illegal. Probably. I'm kind of sometimes I leave it out, like when I'm driving. What's wrong? I'm like, what is wrong? Why do not learn how to ride? I heard signal. I heard somebody else say, was she hungry? Was she possibly be waiting for it? I was like, that's just so. I can say that. I'm like, I'm outside mixed sugar, and they're like, oh, I'm off and on. I'm like, do you not have anywhere to be? Like, go. It was so funny. I was good. That's a good line. It's no right. Yeah. There's just too many people now everywhere. Like, I was reading about they shut down one of the cherry blossom festivals. What? One in one city. Because the tourists are like going to people's homes and demanding that they can use their bathrooms. What? Because they're rude and like. they shut it down in that one particular location because the tourists are so obnoxious. It's not good. I know.
This was gonna happen at the FIFA thing. All these Americans are coming.
Oh,
in
they
and
like walking.
you're like,
Well, you know what, to be honest, though, like, Canadian sporting fans
yes,
are
hockey.
not,
Hockey. Not much better.
not better at all.
No, but here's, I don't
Yes.
And you want to get on the
Yes.
prevention of the mechanism.
Oh, yes.
And then my previous one, I think that was now.
Yes.
Around, which is also better than.
Yes.
If you're forgetting.
Yes.
You need to bring this to the.
Ah, yes.
One feeling of.
Yes, it's very true.
Emphasis.
You got other things like.
It's true, though.
They
No, I thought that me and these people,
at that point.
and we put so much in that.
This way, yeah.
So chemistry teachers are a little bit different from like real chemists who go into chemistry, right? But I know.
I know that.
When I meet with other teachers, I get along best, usually with the other chemistry teachers. Like they're my people. So our personality traits draw us to the same path. Not that I don't get along with other people as well, and sometimes we have differences, but you know how you meet people and you're like, these are my people. They're like me. Oh, have you ever met people like with a personality where you're like, I recognize that personality. I would do things the same way.
I just figured out.
Yeah.
This thing is so off. No.
Oh, yeah.
It's 25.
Yes.
I have to study that. Oh, it's nice. That's why this is.
Yeah.
That's good. Yes.
Thank you.
Because I kind of do.
Yeah. Yes, you're all done with that. All the, I mean. Yes.
Yesterday, I really.
Yeah.
That day was like.
Uh-huh.
Which busy class. So at the very end of the day, I get some of the teams.
Good.
And that's why.
Take care of your mental health. Yes. Yes. Okay, maybe I should be a little easier on you. You work hard. It's all good.
I think so.
See you later. Okay. Oh my God. All right. What am I doing? I am pressing stop. Stop. Stop recording.